So, hello everybody. My name is Andrea Mocci, and I'm here with Jesper Findahl to talk about natural language processing a la Swiss. So, I like stories. I'm going to tell you a little about us because it's important for the context of this talk. Not too much, but so we're from Switzerland in Lugano, and we are from Code Lounge. We are a research and development group, part of the Software Institute at Università della Svizzera Italiana. It was cool this morning during the keynote. There would been a bunch of papers from software engineering research that were cited during the keynote. But I don't do research anymore. We do R&D, so we help companies innovate. And in particular, recently, I also started helping other research groups in other domains to support the research and do like a sort of backbone from the software engineering point of view of their own research. In particular, we work with the Institute of Economics on a project that was focusing on the Registry of Commerce in Switzerland. So the Registry of Commerce helps to track all the data about companies that need to be legally tracked. It could be like a new company being registered, all the people in the board, and stuff like that. And obviously, like most of Swiss things, they are actually recorded in 3 different languages. So in Italian, German, and French, depending on the canton or region. And most of that has been tracked in natural language, pure natural language. So one of the projects that we have is focused on this, and this is why this talk will use these as the main database. And this project recently has been even extended, and we are trying now, together with researchers from the ETH and the University in St. Gallen, and even from partners from Belgium, to actually look not only at the actual data that's been part of the Registry of Commerce from 2001, more or less, that has been digitized, but also to the entries that are available as scanned pages, but they are essentially just, they need some OCR, they need some processing because they were published as a gazette, so as a journal. So in this project, pretty much what we look for is all the data related to companies from 1883, and we want to leverage and we want to extract some information in order to support research in economics. And so trying to reconstruct pretty much the history of the evolution in Switzerland of innovation and the various companies. So this was a little introduction to tell you that we are going to talk about, we're going to actually leverage the Swiss Commercial Registry data in order to learn about natural language processing in a typical multilingual context, so in a very Swiss context in these 3 languages. So I'm going to leave it to Jesper to an introduction to NLP.
Okay. Thank you, Andrea. So for everyone to have a little bit overview what is natural language processing, we will do like we always do, go to Wikipedia. So natural language processing is an interdisciplinary subfield of computer science and linguistics. I have highlighted some of the words that are important for us in the talk. And it involves processing natural language datasets using either rule-based or probabilistic machine learning approaches. So that's what we're going to talk about today. And the goal here is basically that the computer kind of understands the contents of the documents. The technology then can accurately extract information and insights contained in the documents, as well as to categorize and organize the documents. Here we see the so-called periodic table of NLP tasks that we have taken from a blog post. You can see there are a vast set of tasks that you can do, but we don't have time, of course, to all of that, so we're going to focus on a few. In particular, we're going to focus on word parsing, so tokenization, part of speech tagging, and dependency parsing. Then we're going to look at phrases and entities. Here we find rule-based phrase matching, named entity recognition, NER. You will hear that a lot today. Entity enriching, like geoencoding, and also named entity linking. To do this, we're going to use a Python library called Spacy. It is open source and it's free to use. It was released in 2015 and it supports now over 75 different languages, human languages. Lately, they have also added an integration for large language models So we will also have a look at that today. Spacie works by processing the text in a pipeline. So it takes as input the text, and then it does some steps. So the first step, for instance, is usually the tokenizer, which splits the words into tokens, or splits the text into tokens rather. Then we have the tagger, part of speech tagger, that identifies like verbs or nouns and so on in the text. Then, for example, you have the dependency parser that will find relationships between the words. And lastly, in this example, we find the NER component, which takes a word or a group of words and put them together into entities such as persons, locations, and so on. And after the processing, you will get out a doc, which is a Spacie document, which is basically an object which contains the original text plus all these additional information that has been extracted. The dataset we're going to use today, like Andrea mentioned, is the Registry of Commerce here in Switzerland. On this website, Cefix, we find the central business name index, where you can search for any company, and you can find its history. Andrea also mentioned that it's only been digitized from 2001 until today, so before that, it's not available. But here we see some example of a history of a company. They usually contain some information like if the creation of a company or if the board members changed or so on. We'll have now a look at a single entry. Here we see it's related to our employer, Università della Svizzera Italiana. And here it actually describes the fact that we got a new rector last summer. We have highlighted some entities. We have organizations in blue. We have in orange some municipalities or locations, and in green persons. For privacy reasons, we have redacted some of this information. So what we want to show today is how we can automatically then identify these kind of entities. And then we want to do one step more, and is actually finding the place of origin and the domiciles of the people. And you can see it has a specific structure. We find this in almost all of the entries when the person is mentioned, so we will use that. And now I give over to Andrea.
So my role here is to just give some introduction. We picked one of the sponsors of this conference, in this case Red Hat, and I'm going to show you just the basic elements of the pipeline, the most simple ones, and then we'll build it up from that. So I'm going to move to Visual Studio Code on white, just because I think it's a little more readable. I think the font size should be okay, maybe slightly bigger. Okay, I have some bootstrap code that doesn't really matter. It just helps me do the inputs and stuff. I'm going to use pandas for loading and saving some data. And then I'm importing Spacie. One of the important components of Spacie actually does visualization. And we'll see this is extremely useful, especially for some components. I'm also preferring the GPU in order to speed up the inference part. And if you have like even a Mac with Apple Silicon, it's going to work straight out of the box most of the time. So with all the pipelines. So what I'm going to create now, it's a basic pipeline for each of the Swiss languages that we have. So German, French, and Italian. And I'm going to load some models that are predefined models in Spacie. And it's going to take a few seconds, not that much. And then I have these objects. Then I'm going to load, after that, our interesting sponsor dataset. Okay. And I'm going to see like the oldest entries that I have. Oh, I think I've done a mistake, probably. I think that the entries are about JBoss Europe. Do you think this is a mistake? No, right? So you know the history of Red Hat. So actually the presence of Red Hat in Switzerland comes from a company that was acquired from Red Hat at a certain moment. It was actually JBoss. So in the Registry of Commerce of Switzerland, when there was the full acquisition of JBoss, what happened is that they kept the same identifier. So if you look for the identifier that is used for Red Hat, you're going to see also the history of JBoss in the beginning. So if you don't trust me, I'm going to just get the last entries, and you have Red Hat Switzerland from 2022. There might be some newer entries, but they don't matter that much for this kind of analysis. And then you can see, for example, that you have some information like the date of publication of this entry, the canton. So the company is registered in Neuchâtel, so the entry is going to be in French. And yeah, this, for example, these mutation IDs identify the kind of modification that was related to this message, in particular board members or people that are involved in the board of the company. So let's take one particular entry and just take in the last sixth. And this is the sentence. So how an entry in the Registry of Commerce actually looks like. And it says that, okay, Red Hat in Switzerland, SRL, Neuchâtel, there is a number, and then there is, some reference to the last entry that was mentioned in this company. And it says that some people, in this case, Schender Eric Ryan, n'est plus gérant, ses pouvoirs sont radiés, so his power has been cancelled. And then you have a new president, who is Krebs Lurian from the United States. So this is like the nationality. And this is the place where this person lived in North Carolina, USA. So, and then there are some other information, like she has individual signature, whatever this means. Economists will understand this better than us. So now this is a string. If I now apply the pipeline in French to this entry, I get back an object that the default representation of this is still a string. So it looks identical. Well, actually, you have a lot of knowledge. So you can iterate, for example, on this object. And the thing you get, first of all, are tokens. So this works like, the pipeline works really like the pipeline of a compiler, if you want to think it like that. So the first step of a compiler is actually tokenization or a lexical analysis. And so pretty much you want to split the text into words in this case. And this is how it looks like. And obviously, it's not like the rules are so deterministic, like if there is a dot, it's just going to terminate a sentence. Obviously, this dot can have different roles. Here, it terminates a sentence. Here, it's part of an abbreviation. Here is part, for example, a separator for dates. And so these actually tokenizers are way more complicated than the ones you have in a compiler. So that's why this process actually can be very complicated, especially if you have some particular domains where, for example, certain particular things can never be seen by this tokenizer. So you might need to customize them, like we have done in this case. After that, you want to kind of label these tokens to the part of speech. So this does what you've probably done in the elementary school or middle school. Try to understand what is the role in the part of speech for each token. And here, for example, I've taken a sentence in like the second sentence of this entry. And you see that Schender Eric Ryan is exactly three things called as prop n. If you don't know what this means, it's actually pretty intuitive. You can ask Spacey with .explain. It's a proper noun, which makes sense, right? And gérant instead is a normal noun. And that's it. And you have other things like auxiliary, adverbs, but even dates and times and things that identify the type of token. So after that, you can, for example, filter and get all the nouns. And here it's interesting because in between the nouns that you can find, you have really the proper nouns. You have like acronyms like for North Carolina that gets correctly identifies, or United States in French, or even the names of some towns in North Carolina. So this works pretty well. And also this is kind of very domain specific, and it was detected out of the box. It's interesting. This is actually the acronym for the Gazette of the Commercial Registry in Switzerland, and this is the French version. You would have a version in German and a version in Italian, which is slightly different. And it's correctly detected as a proper noun. After that, so the problem, for example, is that if you have a proper noun, like Schender Eric Ryan, you don't want to know that this person is composed of 3 words. You want to identify all together, right? Because these represent a single entity. The same is for Holly Springs, which is a town in North Carolina. These are not 2 different towns. So in order to do that, we can have a component that does named entity recognition. So the basic pipeline I had, it didn't have this component. I can actually add it, and I'm gonna refine my pipeline with this named entity recognition. I'm using a customized one actually, because the versions, the out-of-the-box one didn't work really well, so we had to retrain one. And I'm also doing these merge entities, which are gonna take an entity like a person composed of multiple tokens, and I'm gonna merge it into a single token. This is gonna be useful for something that I will show afterwards. So I'm gonna reapply to the pipeline, and then I can use displace to actually visualize the entities with this style in this entry. If I do that, this is what I get. It's the same text as I had before, but now the visualizer is gonna actually highlight, first of all, the company, Red Hat Switzerland, SARL, the place where the company is actually registered, Neuchâtel, and then you have people, Shander Eric Ryan and Kreb Lurian, from United States at Holly Springs. And as you can see, North Carolina here as an acronym is not recognized as a location. So these tools are never perfect. You might need probably to fix them, okay? In this case, it's quite okay for us. So, and then you can, for example, filter if you want for all the entities and get the people, or you can get the locations separated. So these are all typed. And depending on the component that you use, may have more or less types. So there are named entity recognizer, which are really gonna find very complex entities, but the basic one for our task is more than enough. After that, imagine you wanna do some information extraction. You wanna kind of put it at the second level and of abstraction. Imagine what the compiler does after tokenization. It does parsing. So you try to reconstruct the grammatical structure. And for natural language, this is going to look exactly like a tree. Here, like the visualizer is going to show this tree in this way. So it's quite complicated, actually. So I'm going to focus like on the second sentence here. And here you can see that there is a word that is a root, in this case, Gérant. And then the subject is going to be Shander Eric Ryan, piece is cut, but this is it. And all the other elements, for example, the COP, which means it's the auxiliary to be verb, is also dependent. So it's like a descendant of this root. And this is going to give you information about how this particular noun is linked with all these adverbs and the to be verb. So what I want to do now is, for example, try to link this word, Gérant, to the actual person who is subject. Then what I can do is actually start and finding all the roots that I have. And normally you have really 1 root per sentence. So in this case, you have 4 roots. Each root identifies the entry point, if you want, for a sentence. And here you have, for example, Red Hat, which is the root for the first one. And then you have Gérant, which is the 2 nouns for the second part, for the second and third and fourth sentence. So, yeah, we can focus on the second one as I showed, or like the last one, which should be the 3, which, as you can see, it is also rooted on Gérant, in this case, decline at feminine version, and some other dependent stuff like avec signature individual, with individual signature. If you don't know what are these labelings, you can also ask spacey.explain. In this case, what is n-subj? It's a nominal subject. It's a subject that is actually a noun. So imagine I want to do some information extraction. It's not the one that will be at the end of this talk, but it's kind of related. So the information extraction I want to do, I want to take the roots that are also nouns. So in this case, I would get Gérant and Gérant, the feminine version. And then, for all the nouns that I have extracted, there are roots, I'm going to take the descendants, so the subtree. So imagine really I'm like visiting. The API is not perfect, and in fact, Jesper will show you a cooler way of actually doing information extraction on this data pipeline. But here I'm doing like with just some code, simple code. And then I can get, for example, the people that are subject of these nouns. So in this case, I'm taking all the tokens that are in the descendants. If the token type is a person, and the dependency label is actually subject. So the tree is actually very simple. It's always one node with a lot of children, but it's always labeled with this dependency tag. So this, if they have a subject people, I'm going to take the first one because normally I have only one subject, like in this case. I'm going to check if it's negated. So if its new role is being negated or not. And I'm going to look for all the words that have a lemma equal to ne, which is a negated version, a negated adverb in this case. And lemma is going to actually take any word and reduce it to the form you find in the vocabulary. So for example, it's going to reduce the declination, the plural into singular, the feminine, unfortunately, into masculine, and so on and so forth. In the end, I can print it simply like the subject person, the lemma of the noun, so that it's related to the role, and if it's negated or not. And my fact is, okay, this person is not anymore Gérant, and this person is actually the new one, because this is like negated. So that's it. So as I said, this is just going through some code in a sort of imperative way. Spacie allows actually to do way better than this. I'm going to leave it back to Jesper, so let me go back to the rest of the talk where we do the actual data information extraction pipeline in a better way.
Okay, thanks. Yeah, so in the second part, we're going to look at how we can go from NER to link these entities we have extracted, in particular the municipalities, how we can link them to real entities and also plot them in the end on a map. And also we're going to have a look, as mentioned in the beginning, about large language models and how they can help us. To do this, we have selected a well-known business, Credit Suisse. It is still active in the Registry of Commerce, although it was acquired last year. But the interesting with Credit Suisse is that it's available. We have entries in all the 3 languages. Also, the banks usually they mention a lot of persons in the entries, so this will help us a lot for our task today. Okay, so let's go back to the code. So the first step we want to have a go at is to detect the people with their place of origin and where their domicile in the text. So to do that, we're going to use the phrase matcher. And yes, the starting point here will be the pipeline that Andrea has been building so far. And we're going to take an example entry. This time it's in Italian. This actually refers to a company that was, or a bank that was acquired by Credit Suisse at a certain point. So in our data set we don't only have Credit Suisse, but also its branches and other banks or companies it acquired. So in this in this example here, we can see we have both locations and people. So this serves very well for our purpose. So let's look more into detail about a single person and how this additional information we have now, how it looks like. So we can see, and we use this now to create a pattern. So the first part of our pattern will be a person, which we can find here. It will be followed by punctuation, in this case a comma, the word da, then we have mendricio, which corresponds to the place of origin. Then we have another comma, the word in, and another location, in this case the domicile. Yeah. And now we have this structure. This makes it very easy for us to create a pattern. So the first thing we will do, we create, instantiate a matcher object from Spacey. We give it a pattern that exactly explains what we just had a look at. So the first part is the person, the first token, followed by punctuation, the lower, the word da, another entity here, the location, the place of origin, punctuation, the lower word in, and then we have the entity type of location, which require a response then to the domicile. So we add this to our matcher. We take our example entry from before, and we're going to pass this to the matcher, and then it will give us back all the matches it found. And then we're going to iterate on them and extract the person, place of origin, and the domicile. So let's see what we do, what we get. So in this case, we could see we found the two persons, their place of origin and their domicile. So that's really cool. We didn't have to use any regular expression or something like this, but just with this additional information, we're able to do this. So, okay, that's really good. Now we wanted to take the next step. And this is, we need to somehow find the geo-coordinates of these locations. And to do that, we're going to use something called an entity linking. Basically, we want to link these entities we have detected into some other data set that has more information. Or we can say also we want to ground it into the real world in this case. To do that, we're going to take Wikidata, which is freely available. And here we have basically gotten all the municipalities in Switzerland from Wikidata and extracted some information for each municipality. So we have a unique ID, we have the original name, we have a name and a description in German, French, and Italian. We know its canton, and also we have now the geo-coordinates. So we want to take the entity, link it back to the Wikidata. And to do that, first step is to build a knowledge base. So in our case, we're going to use a very simple one. It's an in-memory lookup knowledge base. You can just think of it as a data structure where you will pass in a given token and it will give you back the information that it has. So in particular, we want to find the Wikidata ID. And what is special or what is good about this is for each of the IDs, we have added multiple aliases of the words. So we're able then with these aliases, to support all the different languages. There are more advanced versions also of knowledge bases where it can also look into the context where it is. So you can imagine that if you want to look for Roger Federer in the text, you have found him, but you're not sure, is it now the tennis player or is it the insurance broker or something like that? So in this way, you can look, maybe there is the word Wimbledon in the text, in the sentence, and then it will give you back then Roger Federer, the tennis player. Okay, we go back. We will have our example entry. And now we are going to get the first location just as an example. We extract it from the document, and then we're going to query the knowledge base for the different candidates for that given location. In this case, it's Lugano. We get back the Wikidata ID plus the name. And now we want to double check, is this really the Lugano we are talking about? So we will open the Wikidata website with adding the QID, and we can see indeed we're talking about Lugano, the city in Ticino. So that's really good. And now we want to automate all this. Of course, we don't want to we want to add this as a component in our pipeline. So we basically just extend the pipeline with another component, which we call the Wikidata entity linker. So I will add this now. And then we're going to take the same example, sending to this extended pipeline. So far, it still looks the same. But now we can query some, get some additional information from each token. So in particular, we're going to look for locations and get their QID or Wikidata ID. So we can see now that we have successfully identified most of the municipalities in Switzerland. We are, you see for Lugano, for example, we have the same ID, so we know we're talking about the same entity. Zurich, we can see it was written in Italian, but it found back the Zurich where we are in now. We also have Mendrisio, and then there's the Riva San Vitale. This is another municipality in Ticino. However, due to the way Wikidata is structured, we were not able to detect that Wikidata ID. So it is missing from our data set. So Wikidata, it works, but it's not 100% correct all the time. Okay, so now we have done this. We have the geo coordinates. Let's see for the next step. So here we want to here the goal is to take all the entries related to Credit Suisse. I think there are around 460 of them. They look, here we have some of them. They are in these 3 different languages. And we are going to, we have read them, and we basically what we have done here, we have processed them before because it takes some time. And then we have we're going to look at the distribution. So we can see they are in the 13 cantons in the 3 different languages, as I mentioned. So that's really good, interesting for our use case. And then we're going to now extract or read in back the domiciles we have extracted using the pattern matching we saw before. We can see that Zurich, most people, when they were mentioned in the entries, they were living in Zurich, followed by Winterthur and so on. And now we can take the geo coordinates basically and plot them on a map. Okay, so here we can see, zoom out a little bit. We can see that, the distribution basically in Switzerland of all the people. We can see many people live in Zurich or around Zurich, not maybe, I mean, that's as expected. People in Basel, also in Bern, Lausanne, in Geneva, also Lugano. So we can see there, maybe we could even say that these are, let's say, the most important bank cities in Switzerland. And now we're going to look at the places of origin instead. And the place of origin in Switzerland is something that relates, indicates where your ancestors were living. So it's something that's inherited. If you become a Swiss citizen, you will get it then. But usually, we will see here also that this follows through generations. So we have a little bit less people from Zurich than before, and overall the distribution changes. So let's see now how this looks on the map. And we can see indeed it's very, very different. No, we can see due to this place of origin, you can see the distribution is very different. It's spread much more over whole Switzerland. And this seems to indicate that people have been moving now into the cities. And now we can compare these domiciles and places of origin. I will put them together on the same map. And first thing I want to just quickly show you is that the number of places of origin and domiciles more or less are the same. I mean, we would expect that it would be the same. However, in Switzerland, you can have 2 places of origin or more even. So, okay. So let's merge these. Let's look at that. and then we will plot them on top of each other. Oh, it's a little small here for some reason. Okay. But we can see here when they're on top of each other, we can really see that it is some differences. So this is really cool. Just by getting the text, we were putting it through the pipeline. Now we're able to visualize where the people are coming from. So this leads now to the last part of this more technical part. And now we want to see how we can use large language models to see if they can help us somehow in speeding up. Like Andrea mentioned, to detect locations or company names like this properly, we have been needed for us to annotate a given set of entries, and also to train or fine-tune a model for named entity recognition. So now I take an example. This is a bank, again bought by Credit Suisse, but we have an example now in German, just to complete all the languages. With Spacie, we can simply define a new part of the pipeline. We start with an empty pipeline. We add the task, the near task, with the location, organization, and person labels. That's what we were looking for. We're going to use GPT version 4, one of the latest versions, to see how good it is. And with Spacie, it's really good because you can just add this to the pipeline, pass in the text, and you will get back a doc object that already has all the entities defined in the right, we can find the exact position of the entities and so on. It takes a little bit longer, but here we see it seems to be doing very well without any, just out of the box. However, we can see here that it's missing some locations. In particular, it seems to be missing the domiciles. So let's see now if we can do better. So we're going to do some prompt tuning or prompt engineering and give the model, the GPT model, some more context. In particular, we will add a description to the labels and their definitions. And then also what have been shown to work very well is to add a few examples. So we'll not show them now, but we have added 2 examples where we indicated which entities are found in the text. Going to again send this to GPT and see what we get back. This way of doing it with having a few examples is known or has been shown to work very well in a paper called Prompt NER. And indeed, we can see now we found the missing domiciles. So this looks really, really good. Seems to be perfect. Of course, there is some caveats using large language model, and that is pricing, because we can't run them on our computer. So here we have computed the pricing for the data set. If we would take all the entries we have, which are around 5 million, and multiply it by the average price we had while building this demo, we're going to see how much it costs. So we're talking around $220,000 US, which is quite pricey, I would say. But also with this, we still don't know how good it is for every entry. Maybe we were lucky with this entry, it worked really well, but another entry has a total different structure and it might not work as well. So what you would need to do is, anyway, you would need to be able to test it and be sure of that. So to do this, you would probably need to create some annotations. And that's what we recommend. You create some annotations, and this could be really good to get a good starting point, would be to use GPT, for example. And we can see with 1,500 annotations, that would be 500 in each of the 3 languages. We're talking about $65, which seems that's a much more reasonable price. So you can have this, train your own model, and so on. Okay, and this concludes now this part, and now I give back to Andrea.
Thank you. So we're like perfectly on time, actually, slightly before. So we have seen a complete pipeline. I want to just recap what we have. So what we have shown to you today, we've seen like the data source that it's like part of our daily job these days to help the economists trying to grasp the history of businesses in Switzerland. And we show how this composes different entries, and these are written in natural language. As I said, from the version on the 1800s gives a lot more problems in this extraction, but pretty much the problem is very similar. Then we've shown like the spacey pipeline actually works, and all these components can actually be constructed and put one on top of each other. And we've seen in the end also how a large language model, a component, can be actually integrated. We didn't see how we constructed some of these custom components, but the API are actually very, very easy to use in this case. We've seen examples of what kind of data structure get extracted, like for example the dependency parser and all the basic ones, and in particular also the named entity recognition with the ability of linking it to real entries in large data sets like Wikidata that can give you additional information to each of the entities that you have like in an entry like this. And we've seen like how you can apply it to visualize it, place of origins and domiciles of people. And this, for example, is useful to economists to understand which areas of Switzerland maybe drive innovation, maybe some unexpected parts, and so on and so forth. Even by certain patterns, recognize who is likely, for example, to be an immigrant and what kind of role he had in certain companies. These are all problems that are open from economists and that can be used with this data. You can actually shed some light. So this is everything for us. This was natural language processing a la Suisse. My name is Andrea Mocci, and with Jesper Findahl. We are ready. Maybe we have time for 1 or 2 questions, or we are around until tonight at the beer time. So if you have any question or you have any problem and you want to know if you can do it with Spacey, we probably can drive you and give you some guidance on that. Thank you very much. Now, if you have time for a question or not. 2 minutes. Only one if there is, but otherwise.
Hey, can you hear me? Yeah. So you mentioned you were using, so at the end we saw like you were using GPT-4 for trying to have an alternative to named entity recognition from Spacey. So I was wondering if you tried also some models that can be locally installed, like Mistral or something similar like that. And I don't know even if Spacey supports that.
So I don't remember exactly. So the API is continually evolving. So probably now there is support for that. When we first tried it, it was only for GPT. Do you know the answer to this question?
Yeah, there are more. You can plug in your own large language model, basically. Yes.
So
okay. And that would make it cheaper.
Yeah.
If you have the infrastructure.
But
yes.
We wanted to, for the demo, we wanted to take the best, whatever. So at the moment, yes. Well, 2 days ago, maybe something else was better. But anyway, for this task, yeah, that was the point to show here that we can be benefited. But you're right, you can use also local ones.
One of the things here maybe is that obviously this large language model seem to work really well only for named entity recognition. For all the other components, maybe for tokenization, yes, maybe even for part-of-speech tagging, it would be cool to see, and now I think Spacey does not support it actually for dependency parsing, because that's the more error-prone part. And that's why actually for the analysis, we didn't actually leverage it. But the example I show you there, it was working well, depending if the sentences are very long, and sometimes these are very long, then what you get out of the box can be can have significant errors.
Thank you.
Okay.
Thank you.
Thank you.